My name is John Hosking. I'm the Dean of Science here at the University of Auckland. It's my very great pleasure to welcome you to the inaugural lecture of Professor Rachel Fewster. Rachel started life as a nature-mad youngster, and after studying mathematics at Cambridge, she returned to nature with a PhD in statistical ecology at St Andrews. She moved to New Zealand for a 2-year postdoc in 1999 and is somehow still here. She works in all aspects of ecological statistics, from applied to mathematical, and runs the Citizen Science Project. Is it Catch IT or Catch It?
It's Catch IT, but if you say Catch It, you have to be very careful.
Yes, that's right. I've always called it Catch IT. Involving several thousand members of the New Zealand public. She's also an enthusiastic educator and has won not one, but 2 National Tertiary Teaching Excellence Awards. One in 2003 as a member of the Stats teaching team, and an individual award in 2009. Statistics is all about making sense of data. The ecological sciences are a statistician's paradise, continually generating new types of data that need to be made sense of, due to a surge in innovative technologies for studying the populations and behaviour of wild animals. Tonight, Rachel is going to discuss some of the questions that arise in the application of statistics to ecology, including how New Zealand's team of 5 million can contribute to not only saving us from COVID, but also to conservation analytics. Rachel will give a taste of the diversity of statistical problems in the ecological domain, introduce a charismatic cast of creatures, and give insights into how we can sometimes convert baffling volumes of data into interpretable conclusions. Please join me in welcoming Rachel to the podium.
Kia ora katoa, and thank you so much for coming here tonight. May I just do a sound check? Is the sound coming across at the back all right? Great, lovely, thank you. Well, it's such a pleasure to see people here tonight. Here we all are at last. This is our 4th attempt to have this occasion. And actually, did you know that technically speaking, tonight is a blue moon? So that is very apt for the occasion. So the title of the talk, Mai I te kakara ki te toara, from sea snails to right whales, a walk on the wild side of statistics. Who knows how to translate a walk on the wild side of statistics into te reo? Well, not me, but fortunately, experts are at hand, and they told me, he tuhurutanga taonga, he haerenga morere, which roughly translated means a statistical investigation, a dangerous journey. So, folks, this is what we're in for tonight, and I will let you know when we get to the dangerous bit. So this is going to be a very traditional inaugural lecture. I'll divulge some background, that means what went wrong to produce me. I will pay tribute to whānau, that's both genetic and academic. I'll rattle on enthusiastically about statistics at great length, and say something controversial and show quantities of awesome pictures. So I'm hoping that I can produce something for everybody here tonight. We've got people from many different walks of life, from conservationists through to mathematicians. And see, there's so many different reasons to be interested in statistics. So I'm going to do my best to produce something that everybody will enjoy. But those of you who are wondering if you might be in the wrong lecture, I'm what's called a statistical ecologist, which means that we're going to be exposed to lots of interesting wildlife tonight, and lots of wild statistics as well. So that's what we've got in store. What is this background? I grew up in Durham in the north of England. Now, as many of you will know, Durham is very famous for 2 things. The first thing, it's got this wonderful cathedral. That was the view that I used to have when I walked to primary school, which was pretty good. And Durham's other great claim to fame, of course, is this character, who's famous for inventing an eye test. Here's a challenge for you. Can you work out which one of these is me? I really can't see how it matters. They're all identical, but for the record, I'm the baby. And as John mentioned, when I grew up, I was wild about nature. I lost no opportunity to scrabble about in the dirt or to brandish my binoculars at innocent bystanders. This fella, for example, I have absolutely no idea who that is. Something went wrong when I was in my teens, and the bug that I caught was actually the maths bug, which is why I ended up studying maths at Cambridge. Now, Cambridge, as you'll know, is famous for many, many things. But what I really want to focus on tonight is the way that we got our exam results, which was like this. And you'll see he's standing there in the gallery reading out what everybody got. Can you believe it? And what's more, I was not the only R. Fewster doing maths at Cambridge in my year that year. I had to wait for the middle initial before I knew what I'd got. And after he's finished reading it out, he just throws all of the listings down and everybody tries to catch them. So much for privacy regulations. So I then decided that although I loved maths, I wanted to apply it to something in the real world. And in particular, I wanted to go back to my hobby, which was the natural world. And I thought that statistics was my ticket to do that. So I did my PhD in statistical ecology at the University of St Andrews in Scotland. And St Andrews, of course, is famous for just one thing, and that is where Wills met Kate. And would you believe my luck? I missed him by 2 years. Life could have been so different. Never mind. These wonderful people were the professors that I knew at St Andrews and still keep in touch with. I would say they're my academic foundation. And I'll just draw special attention to Steve Buckland. He was my PhD supervisor. And he actually was honoured by the Guy Medal in Gold last year, which is something that's only been awarded to 38 statisticians in the last 130 years. So that's a massive accolade, not just for Steve, but for the subject area of ecological statistics. So we were all very thrilled about that. Then I moved to New Zealand in 1999 for a 2-year postdoc. Now, those of you who are good at arithmetic will notice that 1999 plus 2 is less than 2020. So what was responsible for this epic arithmetic fail? Well, I'd have to say it was this fellow, David, who's over there. I somehow chanced upon the best husband in the whole wide world, which in my professional statistical opinion was quite lucky. And I will tell you that this is the most rare and unusual wildlife you are going to see all evening, and that's David in a suit. And of course, you don't just acquire a husband, you gain a whole family, and I couldn't have done better there either. So this is David's lovely family, some of whom are here tonight, which is great. And of course, for pride of place in the Whānau tribute, my lovely parents, and especially my dear father, who died quite recently, and to whom this talk is dedicated. Right, it's time to rattle on enthusiastically about statistics. Let's get started. You must be wondering by this time, what do statistical ecologists do all day? Well, the things I'm going to talk about today can be largely grouped into 3 themes. So The first one, how many are there? What is the population size? And I'm going to spend quite a bit of time on this one because I think it's got a lot of the most interesting and ingenious ideas behind it. The second one, where did they come from? And the third one, patterns and processes, describing what's happened and eliciting mechanisms for what might be responsible for what we see. So let's start off with how many are there. We're going to do a wildlife survey. These are red kangaroos in Queensland. Can you tell me how many there are? Just give you a moment. And the answer is... Okay, so who got 100%? Raise your hands if you got 100%. Now keep your hands raised and just look around a little bit, and you will notice that there's more people at the front than there are at the back. And that's quite a perceptive observation. So we have achieved our ambition. We have an estimated kangaroo population for Queensland. It is 5 per screenful, and that is in fact a valid population estimate. It's a little minimal, I admit, but there's nothing too bad about that estimate. Here they are at the back. You can see now maybe they're definitely kangaroo-shaped blobs on that picture. Now, the problem that we have as wildlife statisticians is, how do we count what we didn't see? That's what the whole subject area is about. Estimating population size means you've got to count how many things you didn't see, as well as how many things you did see, which is tricky. And it's worth going back to ordinary statistics for a moment to think about how ordinary statistics works. So you start off with a question, like, how bent is a banana? Pressing contemporary question. You would then take a sample, and every member of that sample would be somehow informative for answering your question. So, for example, in this case, you could measure the bendiness of each individual banana, and this would contribute to telling you the answer to how bendy is the general banana. Okay. But how could that possibly work here? How, if I see that animal, how can it possibly tell me how many other animals there were that I didn't see? Well, we just have to extend the same principle, and for every animal we do see, we have to collect some sort of information about the chance that we didn't see it, the chance that we might have missed it. So let's have a think about how the survey might take place in practice. You've got an aeroplane going along a fixed flight path, and it's going to see some of those kangaroos, but surely not all of them. And maybe this is what did get seen and missed. So just in slow motion, maybe we see the first, miss the second, miss the third, that one was a tricky one, and see those other two. Now, just as was the case when we did our little wildlife survey in this room, you'll notice that the animals that are close will be easier to see from the plane than the animals that are further away. Which means that if we measure the distance from the plane to each animal, we are actually gaining some information about the chance we saw it. That's how we link back to that kind of archetypal statistics. Measuring the distance to each animal is going to give us some sort of clue about whether it was a more likely or less likely animal to be sighted. And then we could plot those distances, and close distances, we might just have to assume at the moment that we'll see nearly everything, But at high distances, large distances, we know that we're going to see less of what was there available to be seen. And if we can assume that we saw everything we were right on top of, then we can just fill in what was missed. And in practice, we're going to do it using statistical curve fitting. So we'll get a smooth decay. We just need to get a handle on how those sightings fall off with distance. We have to do it that way. We can't just confine our survey to only including the animals that we know we're going to see, because we don't know to what distance that is actually going to take place. So we have to take all the animals that we can see and then do some sort of statistical procedure to account for them. So this is our approach. It's one approach to wildlife surveys, and it gives us a first principle of wildlife surveys, which is, for every animal you see, collect some information about the chance that you missed it. And the second principle of wildlife surveys is, ideally, if you possibly can, collect this information as you go along. In other words, you should measure your detection ability as it applies to the sightings that you have made. Because otherwise, if you don't, and your ability changes, you may wrongly think that it's the population that's changed. So for example, if your ability to detect improves, you will see more animals. You might then think that the population has gone up, but it might mask the fact that the population has actually gone down. Okay? So as to New Zealand's team of 5 million, even for the most rudimentary surveys, it's worth bearing this principle in mind if you can, that we need to know something about our detection ability as we detect animals, as we count the animals we're interested in. Okay, so this was all one method of wildlife surveys, and it's called distance sampling because you sample the distances of animals away from the observer. But this is quite 20th century stuff. We had all this figured out last century. So why are we still banging on about it? What's the active research component of what we're doing here? Well, the thing is that there are lots of animals that we want to count that we are never going to see. They're far too elusive. And this character, the kiwi, is a very classic example of that. We will not be able to fly over a forest and count kiwi. It's just not going to work. Now, it's believed that kiwi are declining in New Zealand as a whole at a rate of 2% per annum. And the government has recently invested $11 million to reverse that decline and convert it into an increase of 2% per annum. Now, I just want to say a couple of things about those numbers. So to start with, 2% per annum might not sound very big, but it actually means that if you continue that decline for just 34 years, the population will be cut in half. Okay, so during our lifetimes, the kiwi population of New Zealand will be gutted if we let that decline continue. And conversely, if it were actually a 2% increase, in 34 years, that population would double. So it's a very small margin on an annual scale, and it has massive differences in consequence on the long scale. And then the other thing is that those two numbers, the +2 and the -2, they're really close together. There's not much difference between a +2 and a -2. So we are absolutely stretching our abilities to the limit to try to be able to distinguish between those two cases on an annual level so that we can work out what's happening on a long term. Where does the 2% decline come from? Well, mostly it comes from volunteers, people just like you, going out on winter's nights and counting calls. And that's wonderful, and actually there's no better way of doing it right now, but it doesn't actually fulfill the golden rule of wildlife surveys, that when you are counting things, you need to be also collecting information about your ability to count things. And because we can't do that yet, we haven't got that function available yet, we can't be sure that it's not people's hearing that's declining at a rate of 2% per annum rather than the kiwi population. So another issue with this is that we can't associate these call counts with any area in space. So, for example, you might think that you've heard 5 kiwi calls, but is that 5 per hectare or 5 per 100 hectares? And that difference is actually quite important, but we've got no way of making that distinction just by counting calls. So right at the moment, we desperately need better ways of doing things, especially if there's millions and millions of dollars of investment going into this. We would love to have better ways of doing it. Here's one of the culprits, a little spotted kiwi, and this is what it sounds like. So you'll notice this is one call, but it's made up of a lot of what we might call syllables, individual detectable units. So imagine if we could do this monitoring automatically, just leave microphones in the bush for weeks on end. Imagine the amount of data that we could get, and imagine if we could take the human out of this whole process so that it's all automatically accounting for not just how many calls we hear, but also our ability to detect the calls that are emitted. Well, this is where we have the 21st century problem. We don't know where the bird is. So we can no longer, if we're leaving microphones in the field, we can no longer work out, unless your microphone is very, very fancy indeed, we can no longer work out where that bird is that we detect on the microphone. So we can't do that conventional idea of distance sampling. What can we do? So this is what the data would look like. It would just be the times at which kiwi syllables are automatically detected by our software. And so you heard that squawk, and then squawk, squawk, squawk. So all we're going to know is the timing at which those squawks arrive at the microphone. That's our data. Then if we've got 2 microphones, we don't know where the bird is, but let's just pretend that this particular bird is a little bit further away from the second microphone. That would mean that the received syllables, the timing would be just delayed by that small amount, and we might miss some of them. So we would go through this timing, and maybe we catch that one, but we miss that one, catch, miss. So it's going to be a lot more muddy, the data that we get from the second microphone, if that bird is further away from that microphone. But that's all we get. So that's what we're going to have to work with. And somehow we want to use data like that to simultaneously assess how many kiwi calls are there and what is our ability to detect them.
There's one at the back.
Is there? So, what do you think? What could we do for that? They're kiwi calls, but not as we know them. So they might be indistinct. They might overlap. You might have more than one bird calling at once. And unfortunately, we don't get this nice colour coding in the data. We don't get calls coloured according to which bird they came from. So what we actually get for our data looks like that. And how many kiwi birds were responsible for that? Well, I do apologise for my enthusiasm here, but this is one of my favourite ever ideas. This is how we could do it. I mean, look at that, isn't that amazing? So what we could do is every time we get a syllable detected at one of the microphones, let's say the first one, so we've got a detected syllable there, what we could do is go to the other microphone and look around nearby and say, what did that second microphone detect close to that first syllable? And then do it for the next one. What did the second microphone detect close to that syllable? And again, for all of the microphone one syllables. So what we're looking at is the intensity with which we receive syllables at the second microphone close by to the syllables we receive at the first microphone. If we find that that's a high intensity, that means that pretty much every time you have a syllable at the first microphone, you're detecting something at the second microphone. That means that they're probably picking up a lot of the same stuff. And that would tell us that detection is not decaying very much over the distance between the two microphones. Whereas if there's a low intensity close by, then every time you see a mic 1 syllable, there tends to be nothing at mic 2. But when you do see stuff at mic 2, maybe there's nothing at mic 1. And that would tell us that detection is decaying very quickly over the space between the two microphones. And therefore, we are actually able to figure out our detection decay over space just by knowing how far apart the microphones are. We never need to know where any birds are. We only need to measure our distance between our two microphones. So I'm really quite excited by this because it's very achievable. It means that using equipment that we already use, you can just leave microphones out in the field and do something with that data. At the moment, we're collecting the data and we've got nothing to do with it. And literally, this data takes up space. It takes up masses of hard drive space, and those hard drives are piling up in people's offices beside their desks, gathering dust, and nobody knows what to do with them. But now we're hoping that we're inching towards a situation where we will be able to do something very useful with them. And the sort of statistics involved in this is point processes meets queuing theory, meets high school trigonometry. So it's a lovely blend of different types of modelling. Yes, so we can do distance sampling without measuring distances, which I think is pretty exciting even. And from confused and tangled data, we can get accurate and precise estimation. That's in principle, and we are still working on the practice. So we're starting with bats, ruder, kiwi, fish, and there's lots of animals that this could be useful for in the future. This is the Quack squad. It's a mixture of statisticians, machine learners, and biologists. And of course, the Quack squad is not quite the right word. We should really call it the Quack, Pop, and Squawk squad. Okay, so that's one method of wildlife surveys. And that covers the case where we never see animals at all. We're doing everything by remote sensing. So now I'm going to go to the complete opposite scenario where we get very, very close to the wildlife. So close that we can identify individual animals. You might have heard the words capture, recapture, and this is what we're going to look at now. So where are we? We are in the subantarctic Auckland Islands in winter, and we have some cold people with cameras, and we have Tohora, southern right whale. These are New Zealand's very own southern right whales. It was remnant population after the whaling of the 19th century, but it's thriving. And very excitingly, we've just had another survey, which I'll show you in a moment. And the thing is, if you can get very, very close and very, very lucky, you can get a photograph that will identify that whale individually by the pattern of barnacles and scars and so on its skin. And that's what it looks like. That's the whale next to the boat. And a mother and a calf. And these are the crew that went there this winter, including two of my favourite collaborators, that's Emma and Rochelle. So very exciting because it's 10 years since the last survey. So we will find out a lot when the data are back about how that population is doing now. So what is capture recapture all about? Well, we have to identify the same animal every time we see it. And that could be by a photograph or it could be by a DNA sample. How do you get a DNA sample from a whale? You have to get lucky. You stand on the boat with a crossbow or a rifle or something, and you fire. And it fires a little dart, just a little dart at the whale, which will just bounce off the whale's back. The whale will barely feel a thing because it's got such thick skin. Glances off it and scoops up this tiny little piece of DNA. And then you've got to try and catch your dart and take it back to the lab. But whatever the method is, somehow we've got to identify the same whale every time we see it. And then you go out and you try to find whales repeatedly. So maybe you take the inflatable out on 6 different days, and for each individual whale, you will know if you saw it on the first day, the second day, the third day, and so on. So you've got this repeated attempt, and that is what's going to tell us how good we are at detecting animals. Our data are going to be those results for all the animals we saw at least once. And of course, that means that we are missing some because we're missing the ones that we never saw ever. But we can analyze this pattern of zeros and ones and fill in the number of zeros to get to how many we didn't see. So it matches with the first principle of wildlife surveys. We've got to, every animal seen, we've got to collect information about the chance that we missed it. We do that by these repeated attempts, the capture, recapture. And the capture, recapture, it does capture usually means see or record rather than literally catch, which would be very dangerous in some cases. And that's where we come to our dangerous journey. So this is the dangerous bit. If you want to run out now, then please do. What's distinctive about that whale? Will you recognize that whale again when you see it? Yeah. It's got these knobbles on the back. So this is knobbly back. But you're going to have to get it at the right angle. You're going to have to be lucky. You're not going to recognize him as knobbly back every time you see him because you might not see the right angle. This one, it's a little hard to see from this photo, but you see how striking that pigmentation is. But once again, this is what we had figured out last century. So what's new? What are we doing about all this today? Well, as we may have recognized, surveys are very expensive, and getting a boat and crew down to the subantarctic in winter for a few weeks is hundreds of thousands of dollars. So while you're down there, you might as well do as much as you possibly can. And if you can take both photos and get DNA samples, then you should. Because why would you pass up the opportunity to collect more data? But that makes it difficult for the statistician because you can't match a photograph to a DNA sample. So let's suppose this is Nobly Beck's true story. This is what really happened. We got a photograph from him on day 1, nothing on day 2, DNA sample on day 3, and nothing on day 4. But we will not be able to observe that. What we will see is 2 unrelated, fragmented records. We'll know that there was one whale that we photographed once and never photographed again. We'll note that there was another whale that we got a DNA sample from once and not otherwise, but we won't know that those 2 are the same whale. And what that means is that if we had these, for example, as the true stories, then what we would get in our data is all these disassociated, fragmented stories. And unfortunately, there's no way we can get back from our data to the truth, because there's not just dozens of ways that this could happen. Every time I propose a way that this could happen, I'm going to give you one pool ball. Not just dozens of ways. If we try to describe all of the possible ways that this could happen, we wouldn't be here all night, we would be here all universe. There are so many different ways you could match these bits of data to individual whales. So what are we going to do as statisticians? We're going to love it, because this is the sort of thing that we enjoy doing, believe it or not. So, too many pool balls is our problem. What do people do in this situation? Well, usually you've got your data, and most statisticians would then set out to find the probability of the data. And then they would adjust their estimates of population size until that probability is as large as possible, and they'd say, bingo, those are our best estimates because they're the best fits to our data. So we're trying to find parameters, things we want to know, population size and detectability, that make our data maximally likely. That's what we're all about as statisticians. But for you, all you actually need to know is that our problem as statisticians is solved effectively when we can calculate the probability of our data quite quickly. If we can do that, we're happy statisticians. But here we've got a problem, because we've got the truth on that side. We don't know what the truth is, and we can't find it out. We've got our data, which is corrupted. We need to find the probability of our data, so we need to get to there on the board, but we can't find the probability of muddled up data. We don't know how to do that. And there's this great chasm between what actually happened and what we observe, and we can't get back across the river. So the truth could be any of those pool balls. We can model the stuff on the left side, but we can't observe it. We can observe the stuff on the right side, but we can't model it. So we're snookered, right? So what do people usually do? Well, they've got somebody on the left side in the river with their with the pool balls, and they pick a pool ball and chuck it across to the other side. I mean, this somebody, by the way, this is a computer program. This is not an actual person. This is not an actual river. This is all conceptual stuff. And they do it again and again and again and again and again. Of course, the statisticians in this room will recognize that what I'm talking about here is Markov chain Monte Carlo methods. You have to make very careful selections of which pool balls you pick that could have been responsible for the data that you see. And you piece together the probability of your data in that way, bit by bit. Now, these are very clever algorithms. Those of you, a lot of you will have heard of Percy Diaconis, for example. It's a very famous Stanford mathematician. He's worked on this very problem. These are not easy things. It's not easy to pick the right balls and chuck them across the river. But they're slow. However well you do this, it's going to be slow. So what we thought was, what if we bush crash further upstream? We go places that most people never really go. We could do something, we could find something dwelling there called the Fourier transform, or if you're a statistician, it would be the moment generating function, basically two very similar ideas. And if you get to there, in the undergrowth, it turns out there's a big shiny bridge that will take you to the other side of the river. So could we sneak in through the back door? It'd be kind of nice if we could, but unfortunately, no, we can't, because there's something even worse in the way, stopping us from doing that. Nobody, if people have noticed that bridge before, nobody bothers to go there because of the crocodiles, basically. So this was, our contribution was that we realized that there was a way of overcoming these crocodiles. And it's called the saddle point approximation. And it's a way of converting from the Fourier transform to the probability that we need. So this is really just for the mathematicians in the room, which is why I had to put a possum there too. But it's an incredibly fast and incredibly accurate approximation. So Joey, who worked on this for his PhD, we've got one model, just one model, where we can get the true right answer. And the true right answer is on this axis, and our approximate answer is on the other axis. And you cannot see the difference. I thought Joey had just made a monumental mistake and plotted the same thing twice because they were so similar, but it turns out it's that good. And this is, and of course we now get our answers in seconds instead of in hours or not at all, because there are so many problems where the pick and chuck method is just too slow to even get an answer at all. And it turns out this is useful all over the place. So, for example, how many people have diabetes in Auckland? You get the same problem of disassociation between GP records, pharmacy records, and outpatients and so on. And we can use this exact same idea here. What's the traffic flow in Auckland? Again, it's actually the same sort of problem again, is because we can only count traffic on individual single links, but we might want to know what's the traffic flow along long routes. And it's exactly, mathematically, it's exactly the same problem. And because of this, it's attracted the interest of two fantastic new collaborators. Martin Hazelton from Otago, he's an expert in traffic modelling. And Jesse Goodman, who's over there, and he's an expert in probability theory and complex analysis. And I am extremely excited because this work that we've done has motivated Jesse to create an entirely new balloon. So it's totally new theoretical work, which it's really wonderful stuff. And we've just got a new milestone between us to develop this. And it happened all because we wanted to count whales by two different methods. So the reason that I wanted to tell you this rather long story is because it shows how amazing what amazing ramifications we might have. As statisticians, applications of what we do can arise in all sorts of unexpected places, which is great. Okay, so I'm going to go to another time and place, and I'm not going to talk about anything so technical anymore. I'm going to show you lots of pictures. This is patterns and processes, and this is Andre from the Brazilian Institute for Amazonian Research, and his question was, what did the 20th century fur trade do to animal populations in the Amazon rainforest? So it was a century or about half a century of unregulated hunting in the 20th century, and that's a warehouse. This is a jaguar looking very unwell, and yeah, that's what it looked like. So this is an example of a case where we have an unusual data set that needs some statistical help. The data were very patchy and generic. It's a whole century of unregulated hunting. They didn't keep great records. But we did manage to wrangle it eventually into an individual species trend for every different species of interest. And Andre then said, would you be able to group the species according to how well they did? So I said, yeah, certainly, here it is. One group did okay, and the other group did quite badly during this hunting era. And then there was a long silence over email. And then Andre said, could you maybe try and do that a different way? Because he didn't actually get the answer he expected. He was expecting that the species that did okay would be the ones that reproduced quickly, and the species that didn't do okay would be the ones that reproduced slowly. But that wasn't actually what the data told us. In the end, it turned out the data told us a very plausible story. It was the aquatic species that suffered population collapse. Why? Because that's where the hunters could get to. The hunters were traveling through the river system, which is extensive, and taking out those animals that they came to. But the terrestrial species actually mostly did okay because they were protected by the inaccessibility of that forest. Except for one species. One terrestrial species did not do okay. What was unusual about this one? This is one of Andre's secret squirrel cameras. It goes around in huge, huge herds, and every so often those herds will cross a stream. And that was when they were taken out by the hunters. So I'll just finish there with a picture from another one of Andre's cameras. This is a jaguar checking it out. Looking a lot more healthy than the last one we saw. And this work was picked up by The Guardian for UN Wildlife Day 2017. And some lovely things. Another thing about statistics is that things that you do in one place are very often useful in other places. And so the exact same methods can be used to reveal genetic patterns in New Zealand beach dwellers. And this can help us to plan and map marine reserves for the future. And finally, we are here at the sea snail with Vanessa, who worked on these. And Vanessa's PhD was 4 years long, but by some marvel of technology, the camera captured her at the exact best instant of it, which was when she handed it in. And isn't that an absolutely beautiful creature? Though given the size of that one, they thought they might have discovered a new species, actually, the tiger's eye snail. Now, for the mathematicians in the room, we are coming close to proving a theorem here. Look at these pictures and deduce. And this is a shout out. You did not know that undergraduate statistics lectures looked like this these days, did you? I mean, what a load of happy looking people. You cannot fake happiness that's sincere and deep-rooted. And I will say that I'm very much looking forward to teaching our new capstone course next year, which will have a lot more of this creative teamwork in. And these students are actually busy making a movie. So if nobody has any questions at question time, I could even show you the movie. So somebody would have to ask for the movie. As you will have deduced by now, it's not a good idea to let statisticians loose anywhere, let alone in the community. But I am sorry to say that that's what we've been doing for the last 10 years, actually, through CatchIT, the computer system for New Zealand conservation groups. And we have about 200 community groups, 2,000 users, 20,000 traps and bait stations, 2 million data records, and a thriving schools program with about 2,000 children so far. So we're going through our terrible twos, as you will have appreciated. And this is the great CatchIT team. And for users, our version 2 is coming very soon now, and you're going to love it, I promise. So watch out for that early in the new year. Have we actually found out anything from all this 2 million data records? Let me give you an example from the Eastern Bays in Auckland, where there's been a backyard trapping program from Orake to Glendowie since 2018. Those of you who've driven through the area any time recently might have seen the boards by the roadside. Well, like so many places, we've had long-term trapping, pest trapping, going on in the local parks. So each one of these is a trap. And since the residents' associations started, we've got a lot more traps. So over 2,000 more traps throughout those Auckland suburbs. And can we detect any impact of that? Well, because we've got all this data, all these 2 million data records going back so far, what we could do is look at the pest catchers in those local parks and see if anything changed around about 2019 when the Residents' Association had taken off. And that's what happened. So there's a much lower catch rate. And the same thing happens with possums as well. These lines here show us what ordinary variability we might expect, and therefore we would have to deduce that something extraordinary happened in 2019. And that's a result of the residents' trapping, I'm quite sure of it. The residential work is removing those pest reservoirs. So people were diligently trapping the reserves year in, year out, and the pests were just coming right back from the wasteland nearby and the residential areas and replenishing those reserves. It's all about source sink dynamics. So it's just like the Amazon. If you leave areas untouched, those populations will thrive and they'll move out into the surrounds. Yes, I'm maybe... yeah, okay, I'll tell you this quite quickly. Here's an example of our graphics. So this is down in the Marlborough Sounds. All pests were eradicated except for mice. And this is a heat map of mouse catchers. Every one of these is a trap. I'm going to show you what happens to mouse catchers inside a fenced reserve when there are no other predators there and you have a mast year, which means heavy fruiting year. So end of 2014, we pick up this video. Early 2015 is a mast year. Watch what happens to the mouse catchers. Deep red means a lot of mice. No colour means not so many mice. And we're going into summer 2015. Bang. That's what all the fuss is about with mast years. And I'm also going to show you the rats in the same place. But I did say there weren't any rats. I said there was nothing left except for mice. But the trouble is that rats can swim. And they do swim very avidly. And so let's see what happened to this reserve in 2 years, starting from nothing, no rats, and then you start to see rats appearing around the coast, and there they go. And as 2016 draws on, those rats are pushing inland, and by the time we finish in about 2017, all of that good work has been undone. We've got a new rat population inside that reserve. 600 rats were caught in the 2 years, starting from nothing since elimination. Which does bring me to the amazing adventures of athletic rats. And I have to include this because I have to tell you a funny story. When rats make an impromptu appearance on an island, we can tell where they come from using genetic analysis. We do this all the time by balancing probabilities. If I told you one of these two gentlemen is from Germany and the other one's from Italy, how many of you would be able to correctly guess which one is which? But for rats, it can work over distances of just 100 meters if you've got a swim involved. And so we go to the Bay of Islands, where the rats were eradicated from the islands in 2008. New rats pop up most years, and genetics confirm that they're local, because this is the sort of camping that you've got on the island. Plenty of opportunity for people to bring rats on their boats and for rats to swim. But then in 2015, the genetics suddenly changed, and we were there first. We picked it up, very peculiar. It seemed like a whole new population of rats had moved in. And Andrew Blanchard from DOC, it's basically his full-time job to keep rats off these islands. And he was led to the source by a stowaway rat. And this is what happened. He was on the beach in the islands giving his customary talk to a load of campers and boaties, saying, watch out for biosecurity, make sure you haven't got any rats on your boat, this is what you have to do if you see one, etc. Okay, anybody got any questions? And somebody said, well, you see that yacht that was moored out there in the sea? Well, while you were talking, a rat just jumped off the yacht, swam onto shore, ran up the beach, and hid underneath that upturned boat on the beach. So Andrew said, no way. But it turned out that was exactly what had happened. So he was able to get the details of the yacht, work out who the yacht owners were, find out where they had launched from, and that was where he found what the source was. So I need to give you a diagram of this because it's sort of a bit hard to get your head around. We've got Andrew standing on the beach. He's talking to all these people. And then we've got this rat which jumps off this boat and it runs in and it hides under there. True story. And that was how Andrew found where those rats had come from. And we blame the pig farms, new pig farms that started up. They must have been shipping rats in their feed and equipment. Okay, well, I think I'm just going to skip one. Oh yeah, sorry, I have to show you our welcome. And for the grand finale, I'm going to skip the controversial thing, and I'm going to go straight to our schools program, which is a collaboration with TFBT, the Forest Bridge Trust. We've got a few people from TFBT here tonight, but they got the acronym wrong because it should have been WFBT, the Wonderful Forest Bridge Trust. It's a fantastic. In fact, they've just been given $8.5 million from the government to demonstrate how wonderful they are for restoring our natural environment. They're called the Bridge because they bridge the east coast to the west coast in the rural North Auckland region, and they're going to build an environmental corridor all the way across from one coast to the other. And they also do a lot of outreach in schools. And we've teamed up with them, and also we've now got uptake in Waitakere as well from Karen Colgan, who's also here. And this is a great program. It's a term-long program for children, and they get experience with trapping using very safe traps, collecting their own data, and then we provide tools where they analyze it, and it's extremely authentic scientific learning for them. You've never seen kids look so engaged with bar charts before, because it's themselves. They're in their own bar charts. And so we, of course, are preserving our statistics undergraduate intake for generations to come, which who could ask for more? And Liz is the star of this show. She's the one that's been going into schools for, 5-6 years now. It's a very, very energetic activity. And it's an absolute pleasure because you get so many kids that just get switched on with this. Maybe they're not naturally very academic kids, but there's something about this authentic learning and the mixture of hands-on and analytic interface that really gets them switched on. So,
Rachel, I just want to say that boy who is looking at me, he's the nearest to the screen there. He was the difficult kid in the class, and look where he is.
Yes.
So it was just amazing.
Did people hear that? So Liz said that this little fellow is the kind of class miscreant. But he was one of those kids that just got really switched on by this. And Liz actually mentioned that she had a lot of difficulty getting them to stop asking questions about these bar charts and making new selections and so on, so that they could go and play the game, which we will see shortly. And we've got a computer game where we're encouraging kids to experiment, think about how they would experiment with different baits and traps and so on. Lots of lovely artwork. This is a self-directed experiment, which is an investigation into the rat-catching efficacy of jelly beans that this girl decided she was curious about. And it's so authentic, because this is unknown to science. We do not know the answer to that question. And we're hoping that by the time we get to 2050, these will be the only predators left in New Zealand that shouldn't be here. So I've got many, many other wonderful collaborators that I haven't been able to feature, and it's a big thanks to all of them, and special thanks to you for coming here tonight and listening all the way through to the end. So thank you very much.
I love my job, you can see why. Thank you, Rachel. We're running over time, but who cares? Got any questions? At the back.
Yeah, can we see the movie?
It's 1.5 minutes. People up for it?
Yes.
Brilliant. Just what I hoped somebody would ask. Okay, so this was a movie made in the space of 1 hour with a budget of $0, and the brief was, make a movie on a topic connected with sample size. And this is what these students came up with. So,
having no luck with the ladies.
Fish eyes, bro. I'm having a real bad year too. Fishes just ain't biting on my hook. I'm having a real bad year. Only 70 babes out of 500 requests.
And real man, I have 7 out of 50. We have the same proportion.
Let's see if it's down to chance. We can say 1 date out of 4 requests seems reasonable for the average bro, doesn't it?
Yeah, that seems fair.
We will make the tally null hypothesis. My distribution will be n equals 500 and x equals 70.
Mine will be n equals 50 and x equals 7. Wow, my p-value is 0.045. Not too bad. I could expect to see that 1 out of 22 years under the null hypothesis.
My p-value is basically 0. That means I could expect to see the result 1 out of 864 million times.
Wow, you really are a loser. Literally hanging out around my crew, making me and my homies look bad.
Sweet nuggets. We appear to have the same proportion with different p-values.
so I reckon there's so much good about that. And you know what? So you will have noticed that that was on a topic called p-values. And it had always been notoriously difficult to get students to understand the impact of sample size on the p-value. But after that movie was made, all of our students expertly answered questions on the impact of the sample size on the p-value, even if they clearly had no idea whatsoever what a p-value actually was.
Do we have any other questions? Yep, Sean.
I'm keen to hear your controversial statement.
Oh, really? Okay, well, I can do that. It will be quick. I sort of wanted to do it. But of course, such is the nature of controversy that I think this is uncontroversial. So, how do you get to professor? At the University of Auckland since 2015, you just need to get 80 publications, 8 grants over 100k, 2 prestigious grants, 6 honours students, 15 master's students, 12 PhD students. Now, a lot of you will be thinking, gosh, that looks a bit idiotic. And all I can say is I don't have very many words except what Thomas Jefferson said. We hold these truths to be self-evident. All publications are not created equal. It seems to me to be the most obvious, plain statement ever. It doesn't matter how many you have, what matters is what's in them. And I do not have those numbers, nothing like them. I had to give up on this university and get an appointment overseas. And it turned out that the university was less keen on that after all, which is why I am here tonight. But, let me just show you this. So let's say you want to get a professor of probability. You want to be a professor of probability, which is more theoretical than what I do. I had it bad enough, but there are people in my department who have it much, much worse. University of Auckland, you need your 80 publications and your what have you. Oxbridge, well, it's much harder to get to professor at Oxbridge, right? Best in the world. Usually 20 to 40 publications is typical to get to professor at Oxford. But they're not actually counting them. It depends what's in them. It's not how many there are. So what we should be doing is not trying to make everybody the same. We should be celebrating the diversity of research approaches. We should be thrilled by non-traditional outputs and assess academic careers on what has been achieved, not by counting papers. So our process for making chairs at this university is malfunctioning. And John is the voice of reason. He's the sole voice of reason. Until about a year ago, he was the sole voice of reason. And he's still reasonable. But we've now got more reasonable people in charge. So I'm really hoping that this is going to change quickly. We have lost excellent staff for this reason. And if you are in a position to speak out, please do, because we don't have any voice unless people say stuff. So, yeah, that was my controversial item.
Perhaps I should just say that that voice came through strongly, apparently, in the submissions for the new strategic plan. One of the things that is being acted on right now is looking at the academic standards.
Oh, great. That's
So,
great. Yeah.
Lisa Erickson and the VC office is actually doing the analysis on.
Yes. Well, I was actually thrilled to see when we had the consultation with the new strategic plan for the university. I was thrilled to see what a strong message it was for values-driven academia. And it's such a breath of fresh air. That's what we need. That's why we're here. And that's how we can make great contributions to society, by pulling together with values, not by counting publications.
Couldn't agree more. So that's a good place to finish, I think. So thank you, Ray.